Okay, so we'll get underway here with our presentation. We're very fortunate this evening to have Dr. Brendan Englot to present his paper on underwater autonomous vehicles in cluttered underwater environments. Dr. Englot has an SD, SM, and PhD in mechanical engineering from MIT. When he went there, as he tells it, he didn't particularly expect to get at all involved in the marine industry. And now he's right in the middle of it when it seems like every other interesting project has to do with autonomous vehicles. So he really got there very quickly. At MIT, he studied motion planning for surveillance and inspection applications, deploying his algorithms, which he developed on an underwater inspection robot that is now being deployed and produced for sale to the U.S. Navy. He was with the United Technologies in their research center in East Hartford, Connecticut, following down where he was a research scientist, the principal investigator in the Autonomous and Intelligent Robotics Laboratory, and a technical contributor to the Sikorsky Autonomous Research Aircraft. He's now at Stevens Institute in the Mechanical Engineering Department. He directs the Robust Field Autonomy Lab, which focuses on robust autonomous navigation solutions for robots operating in harsh and unobstructed environments. And he's the recipient of the very prestigious 2007 National Science Foundation Career Award for Achievement in Career. So with that, I will present to you Dr. Englot.
Thank you. So I'm going to tell you a little bit today about the work we're doing in my research lab at Stevens that is geared toward achieving more robust autonomy in cluttered environments. And these two images kind of typify the problem domain that we're thinking about, where when I say clutter, I mean areas where a robot will have to operate in a confined area where there are low clearances, and the robot really needs to have an accurate picture of its situational awareness in order to avoid collision and plan and inspect an environment like this one. It's also the type of environment where autonomy can be among the most challenging because of the confined areas. So in our lab, we work partially with marine systems. We also work to some extent with ground vehicles as well. Just to give you an overview, these are all the different experimental platforms that we have in our lab. We have a video array, ROV, which is a pretty widely used inspection class, tethered, remotely operated vehicle that's used for security applications. Military and law enforcement use them for harbor sweeps and hull inspections. They're also used by many people in the commercial boating and shipping industry for inspections. We're trying to add autonomy capabilities to the video array so that rather than requiring very intensive manual piloting and supervision using the camera, the vehicle can do its own navigation, and an operator can give it very high-level supervisory types of instructions, like explore this environment and come back with a 3D map of the pier. Then I'll designate which area of the pier to go to for detailed visual inspection. We also have a platform, a surface vehicle platform, the WAMV, the Wave Adaptive Modular Vessel. We just received this at Stevens, and it isn't outfitted with sensors or electronics yet, but we hope that in the next few months we can use these two platforms together to inspect submerged structures both above and below the surface. And for rapid prototyping, we also have a small electric ground robot called the Jackal that has laser range sensing that we use kind of as to practice what happens underwater when we're doing range sensing with a sonar. So what you see in that image is an example of a map we've built using that laser range sensor of the Stevens campus. And the red track lines that you see are the vehicle trajectory that was backed out simply by doing scan matching of all the laser scans. This is something that we also hope we can apply underwater, although the data is a lot more challenging, and I'll talk about some of those challenges shortly. But the image that you see on the right represents a robot that's doing centimeter precision localization just using scan matching of its range sensor. So I'll tell you a little bit about my background. So I did my undergraduate degrees at MIT. Actually, yes, Professor Dedola actually more or less went over this, so I don't need to tell you too much more. other than that I did all my graduate research on underwater vehicles, then had a brief stint working in the aerospace industry thinking about autonomous aircraft with United Technologies and Sikorsky, and now at Stevens for the last 3 years I've been working largely with marine systems once more. But I will tell you I'll tell you a little bit about the hull inspection problems that I worked at while I was at MIT as well, because those kind of set the scene for a lot of problems that we're working to solve now at Stevens. So this is kind of the whole picture of what we would like to be able to do in cluttered environments. In order to be able to monitor the health of a structure, we would like to be able to do that with an autonomous vehicle with varying amounts of prior knowledge. So there might be some situations where we have no prior knowledge of the structure, we don't have a map, maybe the structure is in a damaged condition and we need to go in without any prior knowledge. So I'll talk about the localization and mapping techniques that we use in those situations, which are made more challenging underwater because of noisy data that we're collecting with a sonar. I'll also talk then about what we do as we have evolving knowledge, while we're building this map, how we make decisions about how to continue exploring an unknown environment to gradually put together a complete picture. And then I'll talk last about what we do when we have a prior map. If we have a prior map or a prior model of the structure that we're inspecting, then we can do a little bit better and we can optimize in a number of different ways. And I'll talk about that last. Just to make sure also, can everyone in the back hear me okay? Just want to make sure. Okay, good. So,
I guess it's not conducive. You can always bring up and share over here, although we're still going to have things going out.
So as I mentioned, I'll talk about those three topics. Essentially, first, what to do when you have no prior knowledge. You're going in without any knowledge of what's there. How do you build a map? How does a robot localize underwater? Then I'll talk about how to explore while that map is gradually being built, and then finally how to navigate when a prior map is available. So, this image might not be recognizable to some of you, although it actually was collected at SMPE. So, a lot of the testing of our ROV we perform at the sailing pavilion that you have at SMPE. It allows us to get access to an area where we have relatively low currents, we're safe from most vessel traffic, and there are a lot of interesting submerged structures there for us to inspect with our sonar. So, although you can't see the text all the way back there, on the right you have a corrugated seawall, the interior of your marina, the thing circled there that says our ship's stern, that's the King's Pointer. We deployed our robot from that, and we were scanning the hull. There was another ship dock right next to it. There was another pier perpendicular to the seawall. What you can see here really, though, is just a lot of clutter and a lot of noise. And this is the situational awareness that our robot, the video array, obtains when it goes underneath with the scanning sonar. So we would like to be able to do with this the same localization and mapping that our ground robot can perform with a dense, clean laser rangefinder. And there are some challenges there since we're trying to do more with less. So how can we approach that? Here's another example, a comparison side by side of what we can do with a ground robot and what we can do with our video array. It kind of underscores the challenges here. So on the left you have some playback of our laser scanner scanning around in a public park where we were driving and getting imagery of trees, and we were using these scans, which are all coming in very dense. They see out to 100 meters, and they're coming in at a very high rate. We can just perform scan matching of all of those scans, figure out how much the individual scans have rotated and translated among one another, and we can locate our robot with centimeter precision. So it's easy to do above ground when you have unique identifiable structures like those trees. Underwater, however, with our video array, the sonar is scanning much more slowly, just due to the limitations of trying to see out to 20 meters with a single acoustic range beam, how fast you can rotate in order to build a high-resolution image. The robot is moving while the sonar is scanning. That's one problem we have on the right that we don't have at left. So unfortunately, we can't just take the sonar scans and try to match them against one another. Because even within an individual sonar scan, the robot has moved so much, the contents of that scan are distorted. They don't represent a static snapshot of the environment. So in order to solve that problem, we actually have to pick out individual features from within the sonar imagery. Every single one of those features gets associated with a robot location, and those are used as the basis for building our map and for localizing the robot. So I'll show you what this process looks like with this movie clip here. Let's see. So this shows real-time playback of our video array with its scanning sonar operating at Pier 84, which is the pier that's just across from the Intrepid aircraft carrier. What you see on the left is just the raw data, and what we're trying to do is filter this data and pull out returns from the sonar that represent actual returns of submerged structures. Not only that, but we're trying to pull out ones that are uniquely identifiable that can be used for navigation. What you see on the right are all the features that are being pulled out of the sonar imagery and used to populate our map. The red ones are the ones that have just been pulled out of the imagery, and the green ones are ones that are already located in our map. As we do this, we're finding correspondences among these features and using those to localize our robot. So it might be hard to see if you're in the back, but there's also a blue line that's kind of evolving. That's showing the trajectory of the robot. And right now the robot is being perturbed by about a 1-knot current at this time of day, and it's going to be gradually kind of swept underneath the pier. And you can see the blue track line gradually going closer toward the pier, and the robot will eventually get swept underneath the pier. But the observation and reciting of these features allow us to localize the robot very accurately. In fact, what you can see on the right is that those green points that we're pulling out of the sonar imagery kind of correspond nicely to the geometry of that pier. We don't have a prior model of the pier, so just using some overlay imagery from Google Earth, we were able to verify that we had pulled out a fairly accurate model using this framework. And our goal at the end of the day is not just to localize the robot, but to build a 3D map product that's useful for the purposes of inspection. So what you see at left is the raw data that we ended up pulling out and using to localize our robot. It's still pretty sparse. You know, there are some points, but if the robot wanted to use that for reasoning about collision avoidance, it would be difficult. Then at the right, we have a special type of map that I'll tell you a little bit more about over the next few slides, where we try to fill in the gaps in this data. And in doing so, we're able to produce a more complete and also a little less noisy picture of what the structures look like while the robot was navigating next to the pier. And it ended up coming out fairly accurately as well, just from pulling individual features from the sonar imagery and identifying correspondences with one another. So, I'll tell you a little bit about the process that we use to build those maps. It's been used maybe now 15, 20 years in the robotics field to build a map of an unknown environment if you're sensing with a range sensor. It's giving you the range to everything the robot sees as it's scanning. Take all of the data that you get from that range sensor and throw it into a grid. And as you populate a grid, you kind of mark the individual grid cells as either being free space, where the range beams pass through, the laser or sonar beams pass through unobstructed, or you can mark a cell as being occupied, where the range beam hits something, right, and you got a return from a structure. Gradually, over the course of doing this, the robot will be able to put together a pretty complete picture of its environment, and you have a map that can be used for planning and decision making for a robot that's performing an inspection. So, the state of the art in robotics that has been used for about 15 or 20 years is represented by the center image. That shows what happens where if you just kind of naively assume every cell where a range beam passes through is free, every hit is occupied, and I don't know anything else about the rest of the map, you get a product with a lot of holes in it.
All right.
What we would like to do is take an incomplete map like that one, and we would like to be able to fill the gaps. And so we use a machine learning technique called Gaussian processes to do that, where we try to model the correlation between all those individual cells of the map and beams of the sensor, even if those beams didn't actually intersect those parts of the map. So what you get on the right is a much more descriptive product that kind of takes guesses at what lies in areas that you haven't explicitly seen with the sensor, and tries to make some predictions. So this is an example of what that looks like just over some generic data. Here we just have a simulated range sensor that was sparse, had lots of gaps in it, and the raw data product is shown at left. Using our technique where we try to use Gaussian processes to populate the map, you have the product at right, where we end up making pretty accurate guesses, even if we didn't have complete information. Here's another example with a less structured environment, where we had these pillar-like structures going through. We had very incomplete data, lots of gaps, and our algorithm is able to infer the contents of the map, even in the areas where we didn't have coverage. So this slide kind of tells the detailed story of how we do that in an efficient way. The most important thing to know is that it's not always efficient to model the entire world using a grid, right, where all the cells of the grid are the exact same, very small size. That can be very expensive, especially if you're mapping a very large environment. So one thing that we try to do along the way to save time and to save computational effort is we try to reduce the resolution of our map in areas where it comes into agreement. So even if we're mapping an entire marina or a very large ship with this grid that has lots and lots of tiny grid cells all of the same size, gradually we can pare back the resolution of the grid in areas where it comes into agreement. And that can save additional memory and additional computational effort. So here's an example of what that looks like over two of the environments I showed you. The whole picture of what we were able to do with an experiment that lasted several minutes. The robot was drifting in the water, and it was diving through about 4 meters of the water while it was doing this, scanning out to about 20 meters with its scanning sonar. On the left, you see that complete data set from Pier 84, where we're able to build an accurate reconstruction of the pier. And on the right is a data set from the SMPE marina. So what we're looking at there is the corrugated seawall, where your pier kind of wraps around, and there are these 3 angled sections of the seawall. And the robot was holding station there for quite a long time, but it was able to localize very accurately due to the repeated sightings of these point features that were extracted from its sonar data. And at the end, we build a pretty accurate map from really a very noisy sensor that's giving us very sparse observations of the structures in the environment. And I would argue that the map you see on the bottom right, this is the 3D map we've reconstructed of the corrugated seawall, and there's also a few pier pilings that are visible there. Is accurate enough to be useful and descriptive enough to be useful for reasoning about collision avoidance and about inspection. Going back to the original image of that seawall a few slides ago, being able to build a descriptive and useful 3D map from a product like this is definitely, I think, a step in the right direction toward an autonomous navigation capability. Not only that, but we've developed a few extensions to this. One of the toughest parts of this problem is the computational efficiency. So not only do we want to build these maps from a sonar data set, we'd like to be able to do this in real time. And we need to make a lot of modifications to the algorithm in order to save time. We try to subsample the data. We try to pare back the resolution of the map where we can. And so we're trying to come up with new ways to do this more efficiently. And also have a method that can be stable over very long periods of time. And so now we've developed a method that is a little more stable than it was in the beginning. And even over many repeated observations of the same area, it maintains a consistent map. So that's everything I had to say about how to inspect an unknown environment. I'm curious if anyone has any questions about that. I'd be happy to answer now before we talk about the next steps. I'll also preface everything else by saying this is the area where we've done the most extensive amount of experimental work to date with our video array platform, testing it with no prior knowledge of the environment. You have to have all of these steps of the process working very reliably before the robot can actually start making decisions over these data products. So our emphasis, at least for the first 2 years of our work in this area, has been building these maps accurately and efficiently. Okay, I'll move on to the next part. So I'll talk next about exploring an unknown environment while this map is coming together. There are a number of different ways you can do this, but it is a tough problem. The question is, as you have this map coming together, which again here, this is a map of the structures in the SMPE marina, the seawall on the right, and a pier coming out on the top left. How does a robot make decisions over a map like this? If, after staying still for a few minutes and scanning around, this is the product that I have, how do I decide where to go next? And how do I decide when I'm done? And I hand off the map to the user or supervisor of the system. So there are a number of different ways that we approach this. One of the classical ways to do this is to try driving into what are called the frontiers of the map. Just trying to delineate what the boundaries are between what you've seen and what you haven't, and then trying to prioritize those to gradually drive the robot into the unknown very efficiently to build a complete map. One of the challenges, however, is that this is very difficult to do in 3D. And when you're building a 3D map, these frontiers can be very disjointed. They can be affected by the artifacts of the sensor. And as you see on the upper left, gaps between the robot's scan lines can be misinterpreted as promising areas to go exploring. So what we're trying to do is use the same Gaussian process technique that we've used to build these descriptive maps to also help propose to us frontiers that guide the robot into informative areas. So we have not yet deployed our video array in a capacity where it's making these decisions itself, but we do hope, with all of these mapping tools in hand, this summer we'll be doing a few more of these experiments where the video array will hopefully be making its own decisions about how to explore an unknown environment. There's another way to approach this problem, which is trying to optimize. So maybe instead of saying, how do I go to the best boundary between what I've seen and what I haven't seen, you can ask the question, how do I go to the location that's going to give me the most new information with every single step? And so there's a lot of utility we can derive by thinking of maps as grids and thinking about exploring an unknown environment as how do I grab the largest number of new grid cells that I haven't explored yet or observed yet. So we try to look at that problem as well as an optimization problem. How does the robot take the action that will give it the largest number of new cells, that will flip over the largest number of new cells in this map that it hasn't observed yet? But that's also a very computationally intensive problem. Because as a robot's exploring an unknown environment, even if it's a very simple one like this, I have to think about all the different places the robot might go. I have to project out the geometry of the robot's sensor, and I have to try to count up how many cells of the map the robot's going to flip with each new observation. So we're also applying Gaussian processes to this problem, and trying to inspect that and answer that question in just a few select locations, like the one you see in the middle, and use that data to reconstruct an accurate prediction of what the robot will see and what the most productive places are to explore for every single portion of the map. And that's what you see on the right, is that reconstruction. So what we try to do is choose productive places to draw samples so that the robot can gradually learn where it can take the most informative actions. And one of the tools we use for that is Bayesian optimization, where on every step, we're trying to learn what this information landscape looks like. We're trying to better approximate it, and we're also trying to decide where we can take the most productive sample at every step. This is what it looks like, not for an underwater robot. This is just a simulation showing what the process would look like for either a ground or an underwater robot, scanning that unknown environment with the pillars using a range sensor. And at every step, the robot's looking at this three-dimensional map and trying to answer the question of where can I go next to collect the next sensor view that will uncover the largest amount of information. And we're solving it by taking a very small select set of samples and evaluating it using Bayesian optimization. So this is a long simulation, but if I skip ahead a little bit, well, let's see, can I skip ahead? No, I can only pause it here. But the robot ends up taking productive steps to uncover the map more efficiently than it would if it was choosing it at random or using a different scheme. So this is something we've been able to test in our lab so far. Oops, let me go back. This is something we've been able to test in our lab so far using ground robots. This is just an example of a ground robot we've actually turned loose in our lab, building the 3D map, tasking it simply with the mission of exploring this unknown environment as efficiently as possible, and on every step it tries to collect the next sensor view that will unveil the most new information and flip the largest number of unknown grid cells. And using a strategy like that, the robot's able to make very efficient decisions about how to explore this environment. So you can imagine that this was our video array operating at scanning sonar in close proximity to a pier. It would make very similar types of decisions. And there isn't really any specific structure assumed for this problem or for the map other than that at every step the robot's trying to flip over the largest number of unknown grid cells. So if this is something you're interested in playing around with yourself, this is a software package that we've made available, and using a set of software tools, a free open set of software tools called the Robot Operating System, you can download this and run this even as a simulation. You don't have to have one of these robots to do it. This specific test is run on our system called the TurtleBot. The TurtleBot is just a vacuum cleaner robot, like the Roomba, with a laptop and a range sensor. And using those, we're able to do some rapid prototyping to refine these algorithms before they go onto our video ring. And you can see the robot's continually taking new actions and filling in the gaps, and it's gradually completing the picture of this map, which in this case is just our lab. And there's one more topic in this area that we're working on right now. As I mentioned, deciding how to explore an unknown environment is a difficult optimization problem, especially because we don't know what lies in the unknown and we have to make predictions about what lies there. So one thing that has been very successful in a lot of robotics and computer science has been using machine learning to solve a problem like that by training the robot on existing prior missions, where you've already explored other environments that have the same characteristics. You might have a database of prior maps or ships or peers that you've looked at before, and you can train the robot on those to learn how to make good decisions, so that hopefully when you turn it loose in a completely unknown environment, it will draw on that knowledge to make better decisions. One way that we're looking at doing that is a deep neural network. It's the same way that this is done with images. So, if you give a neural network a whole database of images, it will eventually learn how to tell a cat apart from a dog. Right? And along similar lines, we're giving our neural network tons and tons and tons of prior maps, and we hope that if these maps have relevant characteristics, the robot will learn how to make good decisions about how to explore them, how to avoid collision, and complete the picture as efficiently as possible. The caveat using a method like this is it takes a very, very long time to train a system on prior data sets. You might need to spend several days or maybe even more than a week training many, many, many images and teaching the robot what the best actions were. But the advantage is once you're done doing that, this becomes very, very computationally efficient to implement in practice. And querying a network that has already been trained can be done very, very fast. Faster than any of the algorithms I presented to you on the previous slides. So we're hopeful that if we train our network correctly, we can deploy it on our robots and the robot will make very fast, efficient decisions at a fraction of the computational expense. And that leaves me with the last topic, motion planning, how to navigate an unknown environment when a prior map is available. What can you do to optimize? So, to get into this topic, I'll tell you a little bit first about the work that I did when I was at MIT involving autonomous in-water ship hull inspection. This kind of sets the scene because although we achieved a lot with this underwater robot, there were also a lot of important lessons learned about how to create a robust autonomous system. So, I'm going to play a simulation for you that shows you what we were looking to achieve with this robot. So the algorithms I developed for this robot, the Bluefin hovering autonomous underwater vehicle, which was designed to survey ships of any size. In this case, we're looking at a very large ship, the SS Curtis in San Diego, that has a 7-meter diameter propeller. What you see on the lower left is imaging sonar data of the propeller and the shaft for the stern of that ship. We wanted the robot to be able to go into the stern, which is a challenging area. It's confined and looks different. There isn't one uniform sweep, back and forth sweeping strategy that's going to inspect the stern, like you can use at the forward parts of the ship. So we needed to design an algorithm that could come up with an inspection route that would be as efficient as possible for sweeping the stern of a ship. And as I mentioned, in the forward sections of the hull, things are relatively uniform, flat, and a robot could inspect the vast majority of a ship just by sweeping back and forth in a lawnmower type pattern. At the stern, because there are confined areas, there are occluded areas. If you want to see the cracks between the propeller blades, you need a strategy that can be generalized, and just simply sweeping back and forth might leave some of those areas out. So we actually solved this using a method that's widely used in robot path planning, which is to take a Monte Carlo approach and to draw random samples and kind of keep track of what the robot's seeing in each of those random samples and use those as the basis for constructing an efficient inspection route for the robot to survey the ship. And so although in the beginning it gives you something very random looking, like what you see on the upper right, with continued sampling and smoothing, you can produce something from a Monte Carlo algorithm that looks like what you see at the bottom right, which is a smooth path that most human operators would trust. And it surveys the hull very efficiently. So I'll show you a quick movie that goes through the steps of this planning algorithm. As I mentioned, first, if we want to survey this hull, we draw a large number of random samples to kind of collect viewpoints from different perspectives so that every occluded area of the hull is seen, even the cracks between the propeller blades. Then we use those as the basis for designing an inspection route. First, we try to choose the smallest subset of those samples that sees everything and obtains 100% coverage. And then we try to design a very efficient path that weaves through all of those samples, which is akin to solving the traveling salesman problem. All right? But at the end of the day, this is still an inspection route that's designed in a randomized fashion, and not all operators or supervisors of a system performing this inspection might trust it. So, as a companion method to this, we also looked at where you really needed to use a randomized algorithm to solve an inspection planning problem. What you see on the upper left are actually the toughest parts of the ship to observe with our sensor. These were the most occluded areas where we had to draw very, very large numbers of samples before we could find a configuration where the robot could see these with its imaging sonar. Really, what we learned from this is that you really only need Monte Carlo sampling to observe those specific areas. And if you wanted to, you could design a much more regularized, back and forth, lawnmower type trajectory to observe almost all the other areas of the ship. So at the end of this procedure, we ended up segmenting the ship hull model using lawnmower sweeping paths to observe the planar areas of the ship, and the areas that were not planar we then solved using the randomized algorithm and put the two together so that you could solve any ship hull in as regularized a manner as possible and then solve the remaining really highly occluded areas using our Monte Carlo algorithm. So the big question is, how well does this work on a real ship? Right? So all of this is assuming that we're planning this inspection using a prior model. So where does the model come from? Do we trust it? Is it accurate enough? These are things that we needed to discover and see if we turn the robot loose on a real ship with a prior model, how well can it do? So we had an opportunity to do this on the Coast Guard cutter Seneca, the test in Boston Harbor, where we planned and deployed a full coverage inspection of half of the stern of that ship using the bluefin hovering AUV. So what you see here is kind of a qualitative measure of how well the algorithm did. The blue models are just the prior model that we have. We didn't know how accurate it was. It was produced from a prior survey of this ship that was collected at very low resolution, where all the robot did was sweep underneath the ship, looking up. A lot of areas were blocked and occluded, and we tried to produce the best point cloud that we could to capture the geometry of the stern. Then the robot planned a full coverage inspection using that blue model, and what you see in pink are the areas that the robot planned to see at each of these different locations along the inspection route. So what it was planning to see is shown in pink. What it actually saw is shown in black. Those are the areas. Those are the actual samples from our imaging sonar the robot collected when it was sweeping that portion of the hull. And you can see one thing that worked well is if you do have a good navigation system, you can use a prior model for planning, because the robot did go to the exact locations we planned for it to go to. It was using a Doppler velocimetry sensor for odometry relative to the seafloor. It had a very nice inertial measurement unit that was built using a ring laser gyro. So it had a very accurate navigation system. And using that, it was able to get to these portions of the hull. But of course, what you see here is that what the robot was planning to see didn't quite mesh up with what the robot actually saw. Right? There were some inaccuracies in our model, and we learned exactly where those inaccuracies are. And so you kind of see where there are patches of the model where there's no coverage whatsoever. We learned that the geometry of our model was incorrect. And using this new higher resolution data set that the algorithm allowed us to gather, we were able to construct a higher resolution mesh model, which you see at bottom right, that captured much more accurately the geometry of the stern. So the algorithm worked with some caveats, that planning using a prior model is only as good as that model. And if there are inaccuracies in that model, then your plan will not go as, perfectly as intended. This really inspires a lot of the research that we're doing now at Stevens, where we don't expect that we're going to have a perfect model, and we would like to be able to take account for that on the fly and make changes to account for the uncertainty that the robot's facing, both in terms of having an inaccurate model, not being able to position itself accurately, and also having noisy sensor data. So that motivates this new topic that we're really focusing on in my lab now, which is planning under uncertainty. We would like to go into an environment knowing that there are errors. We would like to try to model them using probability distributions, and we would like to be able to plan as accurately as we can under those sources of uncertainty. And so the image that you see on the right is kind of an illustration of that, right? If a robot has uncertainty about its position, that might play into the path you choose. You may no longer want to take the shortest path if it's one that puts you in danger of collision. And one thing that really underscores this is the data at the bottom right. That's data collected on our video array using our ultra-short baseline acoustic positioning system. And at the origin of this plot, which is on the middle toward the left, that's where our homing beacon is located. And as the robot travels further and further to the right in that plot, every one of those cells is 2 meters, I believe. Yeah. As the robot travels 5, 10, 15 meters away from the homing beacon, the noise level on its positioning system grows a lot in shallow water. It grows severe to the point where the robot really would be in danger of collision if we didn't know exactly what was in the environment. So this real-world source of uncertainty on our video array's positioning system motivates the use of planning under uncertainty. And so one of the things that we work on are developing algorithms that can make guarantees under these types of uncertainty. So what we try to do is model the robot's uncertainty, the noise in its sensors, the noise that's perturbing its actions, all using Gaussian distributions. And we've developed a few search methods that, even under that uncertainty, we can prove that we obtain optimal solutions. And we do so in an efficient way. So just like the Monte Carlo algorithm I was showing you before that was building this large set of samples and trying to construct an inspection route using those samples, we use those exact same constructs for planning under uncertainty. It's just the difference is we try to make projections about how uncertain the robot will be as it maneuvers along that construct. And we try to think about where it's going to be obtaining good measurements, where it's going to be obtaining poor measurements, when its navigational uncertainty will be drifting and growing, when it doesn't have good observations, and take that into account in the planning process to plan past the minimum uncertainty. And I'll show you what that looks like. So this is an example of how our algorithm runs under sensors of differing reliability, and how it plans the shortest path and on the left and the most certain path on the right, the safest path, to get from the bottom left corner of this domain to the upper right corner. So on the left, this algorithm, again using Monte Carlo sampling to build a solution, is just looking for the shortest path. You can see the shortest path just ends up being a straight line on the left side, diagonally cutting across. You certainly don't need to use a Monte Carlo algorithm to solve this type of planning problem, right? But on a large three-dimensional structure, if we're using this to plan an inspection of the ship, we want the algorithm to be scalable. So this is just a representative example of how it would work. On the right, we assume that the robot has better sensing available in the upper left blue region there. So that blue region represents a place where we can either get a good measurement of a navigational feature, we can obtain access to GPS, or perhaps to our USBL positioning system. So in that upper left corner, the robot zeroes out all the error that has accumulated in its navigation system. So this algorithm, trying to plan a path of minimum uncertainty, you can see, takes a detour. It goes into the blue region, zeroes out its navigation drift, and then it proceeds to the goal. And this is not done using heuristics. This is just the result of our mathematical model of the planning problem. And when we draw these samples and perform the search over this graph, it gives us the solution offering minimum uncertainty in the robot. So we're trying to take algorithms like this and scale them to a number of different problems that are relevant both for the video array and for other autonomous systems. Some of these address localization uncertainty. You can also use them to address the amount of risk that the robot is exposed to, either in close proximity to obstacles or in close proximity to known threats. But they have a wide range of applications. One application we've been looking at recently is planning over currents and other challenging marine environment conditions that we can capture using a model. And so we're taking advantage of some of Stephen's modeling resources where they're producing minute-by-minute forecasts of the currents, temperature, salinity in New York waterways, and trying to plan safe and efficient routes for our robot so that it can route itself through currents in a way that it expends the minimum amount of energy and hopefully also stays safe and is able to localize itself with high accuracy. So one example of this is at Wright. This robot is taking a circuit through an area of New York Harbor where there are particularly bad currents at this time of day, and it's planning to go upstream essentially through the area where the currents are the least severe, in the middle between those two red areas, and then it rides the currents back in the opposite direction. And we're hoping that in the next few months this is something that we could also apply on our WAM-V surface craft, so that we could take these models and use them on a real robot to save energy and also keep the robot safe and maintain high positional accuracy. Another element of this that we're working on very recently is learning. So, as I mentioned, you can only do so much with a prior model. There are often going to be errors. It's not necessarily always going to have the resolution that you need. With the ship model, as you saw, there were just some areas that were not accurate, and we had to fill in the gaps with our robot as we went along and revise our plan. Well, similarly, with a model like this, it may not always have high enough resolution. The robot might be gathering more data along the way. We'd like to incorporate that data into the robot's navigation. So one thing we're also trying to incorporate into this process is learning, where hopefully our robot, even though it's facing a lot of noise, can build a better model of the environment every time that it circuits through and patrols a particular region of the environment. And so what we'd like to do is have the robot go in without a lot of prior knowledge about where it can collect the most certain measurements, and as it patrols with every cycle, gradually it gets a better idea of how it can trade off between accurate measurements and navigational uncertainty and energy efficiency. So we call this problem patrolling under uncertainty, where our robot is executing a circuit many, many times. Every time it collects new data, and it makes a revision to its plan, and gradually it learns how to take advantage and find the best compromise between an energy-efficient plan and one that collects the best measurements possible. And another source of uncertainty that we're gradually folding into that picture is currents as well. So here we have a robot that has varying positional accuracy that's reflected by the colors here. So in the blue areas, the robot can collect very high accuracy measurements, and in the red areas, the positioning system degrades. So it's desirable for the robot to stay in the blue areas for the purpose of collecting good measurements. At the same time, the robot's also being perturbed by currents. In the beginning, it doesn't have an accurate idea of where it can go for either resource, and with every circuit, it gradually learns how to patrol and take advantage of both resources. To do this, we're using a framework called reinforcement learning, where basically every time the robot executes a circuit, it gets a score, telling it how well it performed, and every time it gets that score, it uses that to make an adjustment to its policy, which is driving its trajectory through this environment. And our hope is that over a number of cycles, as the robot gathers more data, it will gradually converge to an optimal policy that will allow it to survey the environment using the accurate model that is built on the fly. So that's kind of the scope of research activities that we're looking at. Although we are in the mechanical engineering department, this brings in many tools, from computer science, electrical engineering, and applies them in a domain relevant to marine, naval, and ocean engineers. And so Although that application we find to be one of the most challenging because the data is very noisy, very sparse, and also is collected at a slower rate and bandwidth than the types of data we can collect in air, it represents some of the greatest challenges. And our hope is that if we can apply machine learning tools to do more with that sparse and noisy data, hopefully we can really make an impact in that domain that has been starting to take place in a few other domains as well, ground and aerial robots. So we use a few different robots to prototype the same algorithms. You know, we test them on our ground robot, our underwater robot, and there are very few modifications made from one to the next. We also test our robots in a variety of different locations in the local region, not just at Stevens, but as I mentioned, we've been doing a lot of testing of these systems at the Merchant Marine Academy, an area where we can get access to calm water and have submerged structures that we can map with our sonar. We do a lot of testing also at Hudson River Park. All of the piers along the Hudson River from 59th Street south of there are managed by a nonprofit trust that grants us access to the piers whenever we need to do a test. So that's also a great resource. And we also do a lot of testing at Stevens Pier on the Hudson River. Although the Hudson River has very high currents, and so we have to be very careful about the time of day that we do our testing there. Usually we'll only get maybe a 1 hour window at any given time where the currents are less than a knot and we can operate there safely. We also operate in the Davidson Laboratory towing tank at Stevens. Although we don't need to tow any payloads through there, it ends up being a great test bed for our video array platform. So right now this work is being supported by a number of different entities, some by the Office of Naval Research through the Access Center that's headquartered at Stevens to study surface vessels, some from the National Science Foundation, which, you know, robotics is a very high priority for the National Science Foundation, and they're interested in both the maritime domain and other domains as well. Some through American Bureau of Shipping, through scholarship support we've received, and the new laboratory facility we have at Stevens, the ABS Engineering Center, and some also through fellowships from the Department of Homeland Security. So that's everything I wanted to tell you about, but I would also be happy to talk to you about any questions you have. These are just a few snapshots of us operating our robots out in the field. So thanks for your attention. Yes.
You said the use of this was the hope is for inspection. So are you going to be able to get to the point where you can see deficiencies along the ship's hull?
That's a good question. So I'll go back to the, let's see, the snapshot showing you the sonar imagery that we're collecting. So what you see at the bottom left is really a top-notch imaging sonar. It's a high-frequency imaging sonar called the Dibson, which I think is pinging out to the environment at maybe 2 megahertz. And this is like an $80,000 sensor, and you can get the resolution that you see there, right? So it leaves a lot to be desired if you're looking for a structural defect. That's going to be a really tough thing to see with an acoustic sensor, unless you're looking at very fine resolution and covering a very small area at any given time. So I think the best application we see for this is being a precursor to a detailed visual inspection, where you might already know what your ship looks like, but perhaps if you're scanning a pier that you don't have a prior model of or it might be damaged, you can use that to then point and click on the areas where you would like to do a detailed visual inspection. The robot can go in with a camera and take a picture of a much more targeted area. So that's our hope, because we think, you know, scanning a structure like this with a camera would take a prohibitively long time if you're in turbid water. So you can use this as a starting point to identify the places you'd really like to take a high-res picture with a camera. And maybe as the years go on and this technology improves, we might, you know, get to a point where we can do this with high enough resolution to detect structural defects. But from what I've observed, we've tried with this type of sensor to detect mine-shaped targets, because the Navy, in funding this program, was very interested in mine countermeasures, and they gave us targets that they, you know, represented structures of interest to them that were about the size of a masonry brick. And even with a structure that large, it was very hard to detect those automatically in this imagery, because it is noisy imagery. It's a good question. Any other questions? Yeah.
Is the Navy looking forward to using this on a routine way, or at least,
Yeah.
when do you think that will happen?
So I think the Navy has bought about 15 or 20 of these that
So they're
they
using-
have, they're hoping to continue integrating the routine use of these. But right now they have a very prescribed way in which they're operating them, where they use them only on the forward portions of the ship to do kind of a lawnmower back and forth sweep of the flat areas of the ship that can just be covered automatically that way. They have some automated detection software that tries to detect mines or other shapes of interest. I don't know to what extent they're relying on that. I think they still have an operator monitoring the system, looking at all the data, and kind of calling out if they see anything concerning.
It's a long ways, maybe not a long ways, to be used in the commercial industry on a business like.
Yeah, I would hope so. And I think if we can do it for a smaller platform like the video array, a lower cost platform, because the platform on the bottom left there has so many navigation sensors, it essentially amounts to being about $1 million robot, that a commercial user might not be interested in. If we could get this to work on the video array with the scanning sonar that's a lot cheaper, build a good model from noisier data, we're hoping that might expand the market of people who might be interested in something like this, an autonomous inspection protection. Any other? Oh, yeah.
Did you see yourself be able to have multiple robots at the same time, kind of work together and communicate together?
Yeah.
Can you repeat the question?
Oh, sorry.
In the future, do you see yourself being able to make a community or a couple of robots at the same time, get through a ship, quicker, more information?
Yeah, so that's definitely a goal, because as we tested this, research algorithm, we got to talk to Navy divers who actually perform these inspections. And they do it in quantity. They have a team, and they told me that they go out with 16 divers to inspect an aircraft carrier, for example. So how could you compete with 16 Navy divers if you only have one robot? And not only that, but this robot tops out at about 0.5 meter per second as it's moving along. So it will take a while. If you wanted to inspect an aircraft carrier with this, you would need maybe 8 to 10 hours. And so, to be competitive, really, to make it into the market and be used in this application, you need to be able to do this with a team of robots. And that's a challenge, because communication is a challenge underwater. So if they're communicating wirelessly, they probably need to be doing that over an acoustic channel that has very limited bandwidth. Maybe they're only capable of pushing a few bits per second across whatever channel they're using to communicate with one another. So that's tough, because sharing data is going to be very tough. So you may need to be coordinated. Maybe the robots will have to drop down from buoys at the surface that communicate over Wi-Fi, but the communication aspect of how a team of robots can do this together is a big challenge. Maybe they could all just have a pre-computed one-shot trajectory that they all go to solving, but that's a very active area of research, and it's something we're very interested in as well, is deploying a team of robots to solve a task like this. Any other questions? Yeah.
When you were speaking about building maps in the beginning, and you've got that scanning sonar, how do you filter that? Do you do it on the strength of the return signal?
That's a good question. Yeah, so it's a complicated process. There are many steps in that process. So just to kind of, I'll play this movie clip again to kind of set the scene for how we're filtering it. So one thing that we've observed from collecting this data is that even in one scan, which carries over a very long range, here I think we're scanning out to like 15 meters, sometimes we go out to 25 meters, there are kind of local variations in the intensity of the sonar return. So there isn't always one threshold that allows us to just cut this off and say everything with an intensity higher than this is a structure. Doing that gets you a very noisy map, or if you're too conservative, a very incomplete map. So what we do is we threshold the data first in a very conservative way, where we know we're not throwing out any real structures. Then we cluster it. And so we divide the scan into a series of different clusters using a clustering algorithm. And then we filter each individual cluster using a different threshold that's appropriate to that region of the scan, that has its own local variations in intensity. That tends to get us a better result. Then we cluster that result even further to try to pick out these landmark features that are useful for navigation, that hopefully we can see them and spot them again and again and use them for the purpose of localization. But in short, filtering the data is a really tough problem, and there are a number of different processes that have been proposed for that. We've found this one to be pretty reliable, but that's one of the toughest parts of the problem, is making sure either A, you've gotten rid of all the spurious returns and noise, or B, you haven't been overly conservative and thrown out useful information from the map. So doing it in individual neighborhoods is how we address that problem.
Are there any other universities or colleges who are working on similar research?
Yeah, so in giving you the whole overview, I didn't get to talk about these individual topics in a lot of depth, but yeah, this specific type of problem, there are other universities thinking about how to navigate with sonar. Not as many thinking about how to do it in a cluttered environment where obstacle avoidance and planning are really an important part of the problem. One is, I know, Oregon State University. They do a lot of marine robotics research, and they're also working in this area. I have a few collaborators there. I believe the work on hull inspection has now migrated to Carnegie Mellon University and the University of Michigan. They're also working on this problem. And then,
University of Pennsylvania has a rather
oh yeah, they've got a large robotics lab there. Yeah. They're not much that I've seen from there has focused on the underwater domain as much. Some things with riverine mapping they've done there, where they've fielded kayaks and surface vessels that have done above surface mapping. But yeah, there isn't as large a community of researchers working on this problem as there are for drones or self-driving cars, and so I do think it needs more attention, because this is some of the toughest data with some of the toughest communication constraints. So although the number of researchers is growing, it still certainly would benefit from more attention. But we are the first people to try to build a better map using this machine learning technique. So that's something that we've done that's kind of novel, and hopefully will gain some ground as other people start using it as well. Any other questions?
I would think it would have some significant interest in the naval areas, and go with places that you don't know anything about.
Yeah, absolutely. If those are confined areas or areas that are cluttered, we're hoping something like this could get you a situational awareness very quickly with noisy data.
Okay, well, let's give it back to the regular.